Dr. Tim Stark is a professor of civil and environmental engineering at the University of Urbana-Champaign, Illinois, with an expertise in geotechnical engineering. Dr. Stark has been conducting research and teaching the static and seismic stability of natural and man-made slopes, embankments, and earth structures for over 25 years. He has received a number of awards for his research, teaching, and services. And I will leave it at that. Dr. Stark, you have the floor.
Great, thanks, Chris, and congratulations to Sean and Jason. Great presentation. Your photo of the before and after interchange is really great. So great job. Very interesting project. And glad that Sean started a discussion about drilled shafts, because that's what I'd like to talk about today. And that's a modified standard penetration test for drilled shaft design in weak rock. I heard a comment that you made it down to glacial till, and depending on the strength of the glacial till, the MSPT or modified standard penetration test could be used for that as well. My co-authors, Jim Long, Ahmed Baghdadi, and Reza Osuli. So here we go. What are we talking about? Weak rock. This is unconfined compressive strength material between 10 and 100 KSF. So the photos up on the screen show some shale, so sedimentary rock, weak sedimentary rock. And this is sort of an intermediate zone between soil and hard rock that we were having trouble coming up with design parameters for, as you'll see in just a minute. So we have bumped into glacial till that fits into this 10 to 100 KSF region. So you may bump into it up there in Wisconsin as well. So what's the problem? In a standard penetration test, we drop 140-pound weight, 30 inches. And the split spoon sampler is supposed to go 18 inches. And we used the blow counts over the last 12 to come up with the blow count for that particular test. However, in this intermediate geologic material, we never get to 18 inches. And so frequently we're around 3 inches to 8 inches, somewhere between, say, these two blue lines. And the question is, what do you do with a blow count? And it could be 100. Most people are stopping at 100 blows. And if you stop at 100 blows and you're 3 inches or 5 inches in, is that really a blow count? We didn't know what to do with that number because it's not a standard blow count. So that's what we did. We tried to modify the test to accommodate this small amount of penetration. The red line on the graph right here is 18 inches. So this is really where we need to get to measure a true blow count. Okay, so here's what we need for drilled shaft design in weak rock. We have a tip resistance and a skin resistance, and we need a unconfined compression strength for the skin or the tip resistance. And of course, we add those two up and we get a total. Some DOTs just use tip depending on the project and so on, but even if it's just tip, you still need a unconfined compressive strength. So how do we get the unconfined compressive strength? So here's our blow count problem. And so we were really not knowing how to relate a blow count of 100 with very little penetration, because if you notice, the blue lines I showed you before, say here and about 8 inches, that's about the zone for 10 to 100 KSF material. So we looked at the penetration depth versus the number of blow counts. And so notice we stop at 100. And we notice the curves have sort of two slopes, an initial slope and a second slope that's more consistent. So we subtract out the initial slope here, and what we use is really the slope of this secondary portion. right here. So you'll see in just a minute, we're going to take the slope of this, and that's what we're going to use to relate to the unconfined compression tests we measure. Generally, it takes less than 50 blows to get to this secondary portion. And the reason I bring that up is prior companies wanted to know when they could go into their database, subtract out X number of blows, and they could be in the secondary portion and use those blow counts to get the N rate. And that way their old data could be updated to this correlation, which I'll show you in just a minute. But the rate of this secondary portion is fairly linear because all the disturbed material has been penetrated through, and that's what this initial portion is, some slough and some material in the bottom. So you get a little bit of penetration, and then you're on virgin rock or weak rock, and that's when the relationship gets linear. So we're going to take the slope of this secondary portion right here. This is going to be called N rate or N dot. We now really use N rate, and it's 1 over the penetration depth divided by the number of blow counts that you take the slope over. And because it's a straight line, it's a pretty easy system, and we have a spreadsheet. IDOT developed a spreadsheet for it. So here's the MSPT. We marked the rod, as you can see right here. One way to do it is with a stick rule, as I show here. We've also done it with video cameras. You watch the mark move down, and you hear the number of blows and correlate it that way. But here it is with a stick rule. So we measure the amount of penetration at every 10 blows. So if we were going to go to 100, we'd have 10 of these. But you'll see in just a minute, when you're on virgin material, it doesn't move much. And so you really only need a couple points now. Notice the mark's not moving much at all now. And so it's pretty constant. Now we know we're in the linear portion, but this video goes out to 100. I won't run it to 100. That's Ahmed Baghdadi right there. And you can see again, the mark's pretty well fixed. Driller likes this. They can turn the hammer on. It just goes. If you want to go to 100, it just goes continuously to 100, or we'll stop at maybe 50 or 60 when the mark isn't moving. Okay, so that's the test. So IDOT's developed a nice spreadsheet program for this. Here's the data sheet that goes with it. And you pick the depth that you're at, and notice the blow count 0. So you have the height with 0 blows, 10, 20, out to 100. And this spreadsheet calculates your N rate and QU directly, as well as Young's modulus from the testing I'm going to show you in just a minute. And so here's typical data from one project, two different depths, and you can see run out to about 100. Notice the amount of penetration dropping significantly here, about 0.2, 0.2, 0.2, and now it's 0.1, 0.1, and now about 0.1 out. And notice QU, 6.6 KSF, Young's modulus, and so on. There's the test procedure. It's a test procedure developed for IDOT and available on their website, and it goes into basically the test procedure I just mentioned. Okay, so now we had to come up with a correlation to relate the N rate parameter to the unconfined compression test. So we drilled 21 IDOT bridge sites where we knew we had weak rock, and we drilled 2 borings. One boring was for coring the weak rock for triaxial testing. And the adjacent boring within a couple feet or so, we ran the MSPT test and measured N rate. And then that was able to develop a correlation between N rate and QU. Here's the drilling, rotary wash. Here's the core. So typical core barrel, 2-inch, about maybe 1.5 inch diameter. And that was enabled us to cut the triaxial specimens right from the core, test it, and measure unconfined compression test, or UU triaxial, because we were also interested in Young's modulus. So here you can see some of the core. One advantage of the MSPT is we don't have to deal with broken core, as you can see here, very hard to test. So this is facilitating the development of unconfined compression data. This core, you can see, has a fairly low RQD, and so it is difficult to run triaxial tests. NQ2 or NWD4 core barrels. Okay. So we ran tested 21 sites here. The X's and green stars and red X here give you a distribution of the state of Illinois. There are the different sites, and those 21 sites were used to develop the correlations that you'll see in just a minute. Index properties for the shales, you can see clay size fraction, generally about up to 40, plasticity index to about 20 to 25 here. Dominant clay minerals, illites, and kaolinites. Here's our triaxial testing, and difficult to get intact core out of the core barrel, so that was a challenge. But we did get enough to develop this correlation between MSPT normalized penetration rates, which I'll talk about in just a minute, and unconfined compression strength. So you can come in with your N rate 90 value. If you want it in KPA, you multiply by 4.4 or MPA 0.0044. So let me talk about N rate 90. So we used the safety hammer for all the 21 sites, not the rope and cat head method for running or lifting the 140-pound weight. And we measured the energy in all of the drill rigs being used, and the average energy of all the hammers is 90% of the theoretical energy. So this was really interesting. So instead of N160 or 60%, with these safety hammers, you're operating up around 90%. So the correlation is set up for 90% energy. If your drill rig is imposing 60%, you need to use the energy correction and bring it up to 90% to use the chart. Okay, so that's the correlation. Here's the automatic hammers that I mentioned. So here are the hammer efficiencies. You can see the average about 90, 92, 100, 96, one low one about 77, but all pretty good. Again, if you want to correct your data to N90, this is the expression, and you put the hammer efficiency in and so on. Okay, so how does the measured and predicted values of unconfined compressive strength match? So these are a couple sites where we measured unconfined compressive strength with coring the weak rock, and that's the open symbols here. And then we had MSPT data from the site. We went out and collected it, and our predictions are the dark circles or dark symbols. Same with over here. And you can see there's a little bit of scatter, but pretty good agreement with the measured values. Here are two more. The measured values are the black, and the predicted are the red from the MSPT. Same, the chart on the other side is actually Young's modulus instead of just QU. As I mentioned, we ran UU triaxial tests as well as just unconfined to measure Young's modulus. Okay, so drilled shaft load test, that was the final step to see if the correlation could predict the load test. So here's one of the load tests we ran. It was used an Ostberg cell on the bottom, as you see here. As I remember, this is about 45 feet deep. And we had a prediction, so we had to come up with side resistance prediction before. So we showed up with our prediction. We predicted 7,570 kilonewtons based on the MSPT data we measured at this site. The O cell gave us 7,623, so about a 3% difference. Didn't have the answer beforehand, so we felt pretty good about that prediction. Okay, so here's the design. For skin resistance or side resistance, you can get F sub S in KPA 1.3 times N rate 90, and that's basically using the correlation to unconfined compressive strength. And then for tip resistance, the Q sub T, so you have to multiply that by the area of the tip, is 20 times N rate 90. And these two are correlations for skin and tip resistance are based on load tests that we conducted. Okay, so quick summary, and let's see, how am I doing? Hopefully we'll have some time for questions for not only my presentation, but also Sean and Jason's presentation. So in summary, we think this is a improved drilled shaft design in weak rocks. These are intermediate geologic materials with unconfined compressive strength between 10 and 100 KSF. IDOT, and we think there's some cost savings here because you're using a less conservative QU. You're measuring it in situ directly. So that gives us a less conservative design, less shale coring and laboratory testing. And because of that, there's a shorter design time. This spreadsheet and correlation, you can come up with your values of QU and Young's modulus right there in the field as you enter your penetration depth for each set of 10 blow counts. So IDOT's implementing this through the MSPT test method I showed you, and this spreadsheet that I gave you a quick glimpse of. The spreadsheet plots the penetration versus depth graphs directly, and then it takes the slope of the linear portion directly. So both of those products or deliverables, the test method and spreadsheet, are available on IDOT's website, or if you're interested, I'd be happy to send them to you after this presentation. So I'd like to acknowledge the technical review panel that helped with the project and some external consultants. Bill Kramer was the chair of the TRP. He was head of the bridge group at that time. Brad Hessing, Heather Schopp, Mike Short, Ryan Lanningham, Dan Tobias, Greg Heckel, others. FHWA, Nasser from the FHWA played a really big role in it. Chad Hodel and Terry McCleary were consultants that helped with the project, and Tom Casey as well. Chad developed the spreadsheet for IDOT that I showed. So with that, Chris, I hope we have some time for some questions.